Okay. So this one is kind of a combination of our different Ks, as well as we have our metal forming complexes, and we also have our KSP. So there's kind of a lot going on in here. Right? And so the first thing that it wants us to do is it wants us to find the number of moles of copper that dissolve if our CUI is suspended in 1 liter of water or of solution. So if we are talking about a solid dissolving, which of these are we going to be interested in order to solve for that? Which one has to deal with a solid turning into ions?
The first one, the top one, right?
The first one, our KSP. So that's what we're going to look for. So we're going to take that KSP, and in this case, we can write our expression for that. So we know that our KSP 1.2 times 10 to the minus 12 should be equal to our concentration of our Cu plus and our I minus. Now, both of those are going to be equal to each other, so it really just becomes x squared over on this side. So 1.2 times 10 to the negative 12, and we square root that. This becomes 1.095 times 10 to the minus 6, and that's going to be our moles per liter. All right. So if we think about the number of moles, then it's really just 1.095 times 10 to the minus 6 moles. Okay. Does anyone have any questions on that part? So in this case, it doesn't matter how much CUI we put in, right? We just need that KSP in order to go through and calculate it. So now it says, well, what's the minimum moles of our NaI that we would need to dissolve to fully dissolve that CUI? Now, why would sodium iodide help dissolve our copper?
Common ion.
So if it was a common ion, right, if that was the only thing going on, we'd be increasing our I minus. Would that help more of this copper dissolve?
No.
No, right? So it's not just common ion, because really that would kind of drive us back the other way. But what else can happen there? Right? So if we look at the equations that they give us, what does the copper and the iodine do?
It forms copper iodide.
It forms that that metal complex, right? That ion there, CuI2.
Right.
So that's how NaI helps us dissolve it, right? If it didn't form this metal complex, NaI would not be what we would want to add in. But because it does form this complex, then us increasing the amount of iodide will help us dissolve more of that CuI, because it will change it from being these ions to being one metal complex, which is not associated with our solubility.
So is this where you'd have to multiply the KFs?
So this is where our KF and our KSP kind of have to come together, right? So we get this new equation, which is our CuI solid plus our I minus. Which is in equilibrium with our copper iodide. And so this K expression is going to be our KF times our KSP. So all in all, that becomes 8.5 times 10 to the 4, or minus 4. And now we want all of that copper in that solution to dissolve. We want all of that CuI solid to dissolve. So we know what concentration this CuI2 minus needs to become. Okay? If everything dissolved, we would have 1.00 times 10 to the minus 3 of our CuI2 minus. Because we've dissolved in all of that, we have 1 liter. And we can look at this expression and we can find that our K should be our CuI2 minus over our iodide. And so we're looking for our I minus here, looking for how much of that we need.
Would that just be X minus the moles? X minus 1 point times 10 to the negative 3?
So right now, I'm just finding it in terms of its molarity, but yes, it could be, it would just be your X minus, and then we should have,
Because it's a 1. Oh, it's 2 of them. So
it's 2 to 1. So
it's
we have to remove so much of that I minus, right? But normally for me, I'm just going to find my amount of I minus that I need for my K first, and then I will backtrack and add in how much more of it we need. Right? So this becomes my 1.00 times 10 to the minus 3 over my iodide. I can solve for my I minus. So that's just 8.5 times 10 to the minus 4. Or sorry, 1.00 times 10 to the minus 3 divided by 8.5 times 10 to the minus 4. Right? Now, we do know that some of that iodide that we put in there did get bound up with this copper iodide. So that would be our 1.00 times 10 to the minus 3 moles plus 1.18 moles so it still ends up being about the same. So it didn't really matter, right? Because this amount that we had dissolved was so much smaller compared to how much we need to get in there to get that I minus concentration up high enough to make enough of that CuI.
Wait, you added, not subtracted?
So this is me finding my initial. So if you wanted to make an ice table for this,
All right.
maybe I should have just done this to begin with. Then our ice of our iodide would have been, this is what we're looking for, X. We would have minus from here 1.00 times 10 to the minus 3. And then this is,
X minus.
and so what I had found here, this one is that term. So yes, I'm going to add to it because I'm looking for that X.
Oh, okay.
Right? Because this is my equilibrium. And then this was my
Right, because you're going to find your
change.
initial. So you have to, okay.
And so I need to find my initial.
Use it
But my initial ends up being pretty much the same because I need to dissolve 1.8 moles.
Gotcha.
Mhm. All right. Okay, so we've gotten both of those out. And I will say I do like this problem here where you guys have to figure out how much you need to dissolve it because it kind of combines two of our concepts together, right? It combines our solubility, it also combines our KF. And I think it's a very practical thing, right? You trying to figure out, well, I have this material, it doesn't dissolve well, but it makes this complex. How much of this other thing that dissolves well do I need to add in? I think that's a very useful situation. So I would like to point that out to you guys just so you can think about that. I do think that that is a good thing. All right. So then we're looking at the KEQ for the disappropriation for us turning our copper ion into copper 2+ and our CuS. And so we have our E's and we can use that in order to find our K values, right? Because we can go from our E to our delta G, and then from our delta G, we can find our K. So let's write that one up.
It's asking for that equation or for the one that it had underneath the question?
So it's looking for this new one. It's looking for the copper one. So it's us basically taking our aqueous Cu+ and now turning that into one version of its reducing into a solid, and one version of it's oxidizing.
So the iodide wouldn't play a part in this one anymore?
So the iodide's not playing a part in this one anymore.
Okay.
All right, so we kind of got to know a bit. So we're basically doing Cu plus going to Cu solid, right? So that's a reduction. And we're doing Cu plus going to Cu2 plus. So if we look at our E cell, we need to go ahead and flip our, well, we need to use the oxidation for our Cu2 plus. So that's going to be the negative 0.159 volts. And we're going to add to that the reduction of our copper. And so our E cell is 0.178 volts. So if we want to find our K, then we first need to find our delta G naught. And so we know that we are going to transfer 2 electrons. And we have Faraday's constant. And we have our E cell. And so we end up with something like negative 34.3 kilojoules per mole. Now, honestly, you don't have to put it into kilojoules per mole because we're going to go ahead and take that and turn it into a K, in which case we're going to need it in joules again, so it doesn't really matter. And if we want to find our K, then we can take our E times delta G over RT. So this becomes E to the negative 34,300 joules per mole. Divide that by 8.314. Divide that by 298 Kelvin because we're at 25 degrees Celsius. And so we get a K of 1.05 times 10 to the 6.
Could you just have taken your E cell and then divided it by NF over RT and then taken the natural log of that instead of finding delta G? Isn't there an equation that's
I see what you're saying. So you just set E.
It's not, I don't think it's negative in this case.
Yeah, this one should become positive because we moved over.
Yeah.
Yeah, you could have also done that. So that should be our 0.178 times 2.
I don't know if it equals the same thing.
Yeah, so you could have also done it that way as well. Both of those work. Okay. All right. Now, going back, how do I go back? The last part is that it says that our metal iodide is not stable, right? And so it wants us to describe the decomposition of it in an aqueous solution, and then show that it is a spontaneous reaction. So that's kind of us looking at our decomposition of that copper iodide, right? So it's us taking CuI2 minus and then having it decompose, right? So we're going to make some space. So CuI2 is going to break down into kind of 2 processes. We're going to get copper ions out. And we're going to get 2 iodines. Now, those 2 iodines, those can do 2 things, right? If we do our copper iodine as a solid, right, which is what we started off with as we decomposed everything else, then we can also make I2 material that's going to come out. So we can kind of think of this as being our Cu2 plus I minus going to Cu plus and I2. I guess we should balance that. And then on the other side, we can have a, well, and so this is going to be our redox. And so I kind of got this equation by looking at our looking at our bottom three of our looking at these three down here, right? You can see that our copper 2 can turn into our our Cu plus. We can also see that our Cu plus and our iodine can turn into our solid up here. We can also see that we can take our I minus and turn it into the I2 with whatever we have left over, right? So it's kind of like a combination of pulling those together. Now, I did think that this was a little bit advanced to have you guys figure out the whole like decomposition one. So I think that that part's not necessarily ideal of a situation. So I probably would have expected them to give you more guidance about it. But now if we're looking at part 1, if we have this equation, how can we tell if it's going to be spontaneous or not?
Calculating the delta G.
So we need to find the delta G. And so if we want to find the delta G for this one, what do we need?
The E cell.
The E cell. So our E cell here should be that copper oxidation, but this time it's going to be a reduction. So 0.159 volts this time instead of the negative. And then we're going to use the oxidation of iodine, so minus 0.540 volts. And this process exchanges 1 electron for us. So we should have negative 1 times 96485 times our E cell, which in this case is going to be 0.159 minus 0.540. And so we get 36.8 kilojoules per mole, which doesn't seem very spontaneous. But there is a second aspect to this, right? Is that those ions that we make could also turn into that precipitation. So Cu plus to our solid once we get to a certain concentration of them. And because the solubility is fairly low, we could get there pretty quickly. And so we need to look at that delta G. And so for that delta G, we're going to use our RT ln of K. And luckily, we already found K, so that should be negative 0.008 R. .314 times 298 times the ln of our one of our KSP. Now we're using the 1 over the KSP because it's the opposite of our dissolution equation, right? So we should be going the opposite way. This is the precipitation. And so this ends up being negative 68.0 kilojoules per mole. And that seems like a very spontaneous process. So we kind of have these two things going on. So if we want to find the delta G for both of them together, reaction 1 and our precipitation of reaction 2, which when we look at that kind of gives us the copper 2 plus our 2 iodine. It basically ends up giving us this equation here. We kind of have our 36.8 kilojoules per mole plus negative 68.0 kilojoules per mole. And so we get a spontaneous reaction, which is that negative 31.2. Right? So what I would say is that I would have expected them to give you a little bit more guidance about this top equation here, because this one was relying a lot on you kind of taking it, breaking it down into the ions, and then looking at all the possible equations they gave you about where things could go from that, right? That, okay, well, we could redox it. And then once we redoxed it, then we could have whatever was left over to turn it into that solid. So we could have a precipitation one, which is kind of a lot, right? That's a lot going on with that one. But if they had given us to this point, right, where they helped us figure out what our products would have been, then we could identify that, yes, we should have a redox equation going on because we have to make it into that copper ion. And then we should have a precipitation reaction because if we have that copper and that iodide and we know that the CUI is not very soluble, if we got above a certain concentration, we would expect to see it come out. And so we could figure that part out. Right? And so just keep that in mind of kind of where my expectations would be for where you would want to be doing with this question. Does anyone have any questions on that part? So right now it's 9 o'clock. I don't want to keep on going through more problems because I don't want to have you guys run out. I want to make sure that we're able to start the ACS on time because I do know that some of you guys need to kind of start it at 9:30 so that way you guys will have enough time. And I know you didn't necessarily block out more time than that. I will remind you that I do have a review this afternoon during my office hours, 1 to 2:30. I'll go over some more of those then. I'll record that session and also put that up onto YouTube as well. So if something does come up and there's a specific topic that you want to see, so if there's one that you didn't see now that you would like to see, then put it in the chat and I'll make sure to go over that this afternoon. And if you can show up in person or if you can zoom in, I'll also take questions for that then as well. But I just want to make sure I give you guys a little bit of time to mentally prepare for your ACS because you guys do have that today. Now, for the ACS, you won't have to worry about submitting scratch paper. You can submit it, but to be honest, there's very little partial credit that's going to happen for your ACS because the style of test it is really more about using sheer number of questions to kind of get to the right curve, right? What I would say for your ACS exam is there will be a curve for it, right? I look at the norms of what they expect things to go for this one, and then I look at how our class did, and so I can go through and I can norm out kind of based on our performance. You will not have to get 90% of the questions right in order to get an A. I can almost guarantee you on that part that it won't go in that direction. So I'm not exactly sure where that cutoff would be, but if you think about it, if you get something like 59 of the 65 questions right, you're probably sitting very solid. So just keep that in mind when you go through your whole exam and you guys see your raw score at the end, that won't be what your final grade will be for your exam. There will be some curving that happens afterwards. And so what I would recommend is just as you go through, make sure that you don't get stuck on one question for too long, right? Answer as many of the questions as you can first, and then come back and deal with the ones that take some more calculations, and then make sure that you put an answer for every single question because there is no penalty for guessing. And so even if all you can do is eliminate 2 of them, then there's still that really increases your odds. So like things for like titrations, right, or buffers. If you know that this buffer is going to be on the acidic side, then you should be able to take out some of those answers, right? So you can get an idea about where that is. Right? And so just keep that in mind as you kind of work your way through your problems. What I would say is the hardest part that people struggle with this exam more than what's very different than ours is time is a thing. You have to make sure that you're moving along because otherwise time can very easily run away from you because you don't get very long for each question. So just keep that in mind as you're kind of working your way through this.